Um, so our final speaker today is Professor Terence Tao, and I've gone through the whole world of nationalities. Professor Tao is back to the origin almost, is an Australian mathematician working on diverse fields such as harmonic analysis, partial differential equations, combinatorics, analytic number theory, and representation theory. A child prodigy, Tao taught older kids numbers and letters when he was 2 years old. Being asked where he knew numbers and letters from, he said, from Sesame Street. At age 13, he became the youngest winner of the gold medal at the International Mathematics Olympiad. He received his PhD from Princeton University at age 20 and became full professor here at UCLA at age 25. His list of awards is so long that I will restrict myself to listing only awards that he received within the last 12 months. So, among them, the Fields Medal 2006, the MacArthur Fellowship, the Sastra Ramanujan Prize, the Ostrovsky Prize, the Jim and Carol Collins Chair of the College of Letters and Sciences, and one of the top 10 brilliant scientists of the Popular Science magazine. And I hope I didn't forget any. And it's now my great pleasure to introduce Professor Tao, who will speak on Nilsequences and the primes.
Thank you, Christoph, and thank you very much for coming here. So I'm going to be speaking about recent work in prime number theory, mostly focusing on what I did with Ben Green at Cambridge in the last few years. So what Ben and I work with is an area, okay, that's not so nice, an area of number theory called analytic prime number theory. So it's a study of the prime numbers, 2, 3, 5, 7, just prime numbers, but not so much like figuring out which numbers are prime, which ones are not prime, but figuring out things like more quantitative things, like how many prime numbers are there, say from 1 to n, what kind of patterns are there in the prime numbers, things like that. It divides into two main branches because there's sort of two interesting things you can do with prime numbers. You can either multiply prime numbers together, or you can add them together. The two branches are actually quite different. In many ways, it's more natural to multiply prime numbers together. I mean, prime numbers, the definition is a very multiplicative definition. Prime numbers, one which can't be factored into smaller numbers. And hence, actually, a lot more is known about the multiplicative structure of prime numbers than the additive side. But there's been a lot of progress on the additive side, too. So what Ben and I do is mostly on the additive side, but just for reasons of analogy, I wanted to describe also the multiplicative side of the subject. So multiplicative number theory, let's see how does this work? Yeah, so multiplicative theory is a theory of how to express a number as the product of prime numbers. So like how many prime numbers are in the product of a given number, or like if you divide a number by a prime, what kind of residual class do you get? Yeah, like if you, for example, divide a prime by 10 and you look at the remainder, so the last digit for prime, what does the last digit for prime look like? That's a question of multiplicative prime number theory. Additive prime number theory is a theory of adding primes together or maybe subtracting primes together. So like how can you write a number as a sum of prime numbers, as the difference of prime numbers? And closely related is whether you can find patterns, additive patterns, like arithmetic progressions in the prime numbers. Okay, let's see. So just to give you some examples of the type of results that we know about, here are some results from multiplicative prime number theory. If you take a really big natural number n, so whatever, like a number of size 1 billion, and you ask what does it do, like what kind of properties does it have? Well, it depends on n, but you can ask statistically, like for all numbers in a certain range, say between 1 billion and 2 billion, what tends to happen with a large number. And so here are some classical facts. For example, if you look at a number and you ask how likely is it to be square-free, that means that it's not divisible by any square, 4, 9, 16, other than 1, of course, every number is divisible by 1. But to be square-free, that happens basically exactly 6 over pi squared of the time. It's an interesting fact, and that's due to Euler. It's a fun thing to teach in an undergraduate class. So that's one fact. Another fact, 100 years later, Dirichlet computed how many factors a big number has, and on the average, it is the natural log of n. So if you know that a number is of size 1 million, you know that it has roughly log 1 million, so 10 or 12 factors on the average. And they're very precise versions of that. If you take a large number, it's not very likely to be prime, but we know exactly how likely it is to be prime. A large number n, picked at random, will be prime about 1 over log n of the time. If you ask not how many factors you have, but how many prime factors you have, then it's not log n, it's actually much smaller. It's log n. Log n, just a side note, this is, if you graph this function, it goes to infinity as n goes to infinity. So the bigger your number, the more prime factors you're going to have. But I think Karl Pomerantz, a great number theorist, once said that although log n has been proven to go to infinity as n goes to infinity, no one has ever observed this in practice. So, it's really hard to come up with a number, say, with 100 prime factors. And it doesn't happen very often. Okay. So that's multiplicative number theory, prime number theory. If you go to additive prime number theory, what you start finding is that the results are fewer, and in fact, many of them are conjectural. So, all those results are proven. Here are a typical some results from large prime number theory. If you take, again, a very large number n, we know, for instance, that any large odd number n can be written as the sum of 3 primes. This is a famous theorem of Vinogradov from 1937. It only works when n is large enough. There is a conjecture, it's called the odd-Goldbach conjecture, that in fact every odd number bigger than 7 or something should be the sum of 3 primes. But it's not known that all numbers, only all big numbers. What does big mean? I think the world record right now is all numbers bigger than 10 to the 1346. All odd numbers that are that big or higher are sums of 3 primes. So there's a gap that people are still trying to fill. What else do we know a big number n? So there's a famous conjecture, the twin prime conjecture, that we know that there's infinitely many primes, so we know that n can be prime infinitely often. But it's also conjecture that not only can you be prime infinitely often, but you can be prime and also 2 less than a prime. So you can be prime and also next to a prime. So you can be part of what's called a twin prime. And that should happen infinitely often. This is perhaps one of the oldest conjectures maybe in mathematics. It's conceivable that Euclid back in 300 BC thought about this problem. And it's just but this is an additive problem rather than a multiplicative problem. And as such, we still can't solve many of the basic problems in the additive field, even though we know a lot about multiplicative. Yes.
What is almost prime?
I'll come to that. So the twin prime conjecture we can't prove, but we can do some things. So the closest result we have on the twin prime conjecture is a result of Chen in 73, that while we don't know that there are infinitely many primes that are next to a prime, we do know that there are infinitely many primes that are next to what's called an almost prime, which is either a prime or a product of 2 primes. It's a number with at most 2 prime factors. So that's about as close as you can be to being prime without actually knowing that you're prime. And so we do know that there are infinitely many primes that are close to an almost prime. There is a very important reason why the proofless theorem does not extend to something called the parity problem. It's very hard to tell apart whether you have an even number or odd number of prime factors, but that's another story. And then, of course, you may have heard of the even Goldbach conjecture, which is that every even number, in particular every large even number, should be the sum of 2 primes, every even number bigger than 4. And so that's an old conjecture of Goldbach, I think dating to 1780 something. Okay, at one point there was even $1 million prize attached to this. It's expired now, but it would still be very good to do that. This is about as hard as the twin prime conjecture. See, the twin prime conjecture is telling you that 2 can be written as the difference of 2 primes. And the Goldbach conjecture is telling you that any large number can be written as the sum of 2 primes. And they're almost the same type of conjecture. But we can't solve either of them. Okay, so that's that. So multiplicative and additive number theory, they use very different techniques. So if you want to understand multiplicative problems, like multiplying primes together, breaking up numbers into factors and so forth, it turns out that what you really have to do is that you have to understand not just what the primes do, but you raise a prime to an arbitrary complex number s. You look at Peatley s, and you ask what does Peatley s do? Like what does Peatley s look like on the average? How is it distributed? If you sum all the Peatley s's together, what do you get? This type of. It turns out that knowing what the powers of Peatley s do will tell you eventually what products of primes do. And the reason it's a bit complicated, but it's ultimately due to this little algebraic fact that the product of two primes raised to the s is just the product of p to the s and q to the s. So if you understand p to the s and you understand q to the s, in principle you understand what p q to the s is doing. So if you understand what the primes to any s are doing, then you know what products of primes to any s are doing. And if you do that notice for every s, you can start doing some sort of contour integration or Fourier analysis, and you can get. And this idea goes back to Euler, and it leads naturally to this wonderful function, the Riemann zeta function, zeta of s, which has two nice representations. It's either the sum of one of entity s. It's actually the discrete version of what Richard's renormalized integral is, integral of 1 of x ds. You take sum of one entity s, you get a very similar function in some ways and very different in other ways. Because of the of arithmetic, this sum can be written as a product over primes, and you see the p to the s there. And so in principle, if you understand zeta, then you understand what p to the s is doing, except that because there's -1 here, you actually need to understand 1 over zeta to the s in order to understand the primes. And so you need to know when this thing is 0, and that's a really difficult problem. That's got to do with the Riemann hypothesis, which no one really has much of a clue what to do with, including us, so we don't have anything to say about the Riemann hypothesis. This is multiplicative stuff. So we instead work with the additive theory, but I just want to put this up because it's it's very well known, this Riemann hypothesis. Okay. So we instead work with additive problems. For example, the go-back question is what numbers are sums of primes? And if you're working with sums of primes rather than products of primes, it turns out that all this Riemann zeta function stuff turns out to be, well, not useless, but far less useful than we'd expected. So even if we have the Riemann hypothesis and various generalizations of the Riemann hypothesis, we don't get things like, we don't advance anything on the twin prime conjecture or anything like that. The Riemann hypothesis, if you solve it, it would be fantastic. You would get really good understanding on any multiplicative question you please, but it still doesn't say much about the additive questions. It says a little bit, but not a dramatic amount. So for multiplicative problems, you want to understand p to a power. For additive problems, you want to understand a power to p. So here what you do is that you look at things raised to the power of p. So it turns out that a good thing to do is actually raise complex numbers to the power of p. So e to the 2 pi I alpha p, where alpha is just some real number. In number theory, we often abbreviate e to the 2 pi I. We see it so often. E to the 2 pi I x is called e of x. So this expression here, we abbreviate e to the alpha p. So if we can understand what this is doing, one way to think about this, and I'll turn to this later, is you have the circle, and alpha is some angle. And so you can imagine starting at 1 and rotating by alpha, and rotating by alpha, and you're going around and around in a circle, and you have all these points in the circle. So imagine you don't take every point, but you just take the prime points. You take the second point, the third point, the fifth point, the seventh point, the 11th point, and so forth. That gives you some subset of points in the circle. And knowing what those points are doing is actually equivalent to understanding what this number is how this is distributed. And this turns out to be really key. The reason why this is important is because this expression is connected to, lets you understand sums, again, because of this identity that e to the alpha p plus q, this expression of p plus q is just the product of e alpha p, e alpha q. This is one of the laws of algebra. So if in principle, if you understand exactly what this expression is doing and this expression is doing, you understand what this is doing, and then using Fourier analysis or something, you can then understand what p plus q is doing. So we really want to understand this expression, how it's distributed, and in fact, so rather than the zeta function, in fact, what attention is focused on is something called the prime exponential sum. You sum e to the alpha p for all p primes p up to some number n, and if you understand this well enough, in principle, you understand this expression, and in principle, you can understand things like sums of primes. And this whole approach has a name. It's called the Hardy-Littlewood-Vinogradov circle method. And for example, this is what Vinogradov used to prove that every large odd number is a sum of 3 primes. It actually is based on this approach here. Okay. So now let's contrast two results, one from multiplicative number theory and one from additive number theory. So here there's a sort of a nice symmetry. There's a result, old result Dirichlet, concerning primes and arithmetic regressions, and that's the result in multiplicative number theory. And then there's a recent result of Ben and myself not on primes and arithmetic regressions, but on arithmetic regressions and primes, and that's an additive result. So I just wanted to put them up on the same screen. So the result of Dirichlet is that if you take an infinite arithmetic progression, so that's, in other words, a residue class, you take some modulus q and some number a. For example, q could be 10 and a could be 3. And so what you're doing is you're taking all the numbers which, when you divide by q, give you a as a remainder. So all the numbers which we divide by 10 give you 3 as a remainder. In other words, all the numbers which end in 3. So that's an infinite arithmetic progression, 3, 13, 23, 33, 43. Some of these numbers are prime, some are not prime. Like 3 is prime, 13 is prime, but 33 is not prime. But Dirichet's theorem is that any one of these infinite arithmetic progressions will contain lots and lots of primes. It will contain infinitely many primes unless there's an obvious reason why they don't. And the obvious reason is that a and q have a factor. Like if you look at all the numbers that have a last digit of 2, 2, 12, 14, sorry, 2, 12, 22, 32, 42, they don't contain, they only contain one prime. That's because 2 has a common factor of 10. So there are not infinitely many primes ending in 2 or 5 or 6, but there are infinitely many primes that end in 3 or 1 or 7 or 9. This is Dirichet's theorem. So arithmetic progressions contain lots of primes. Our result, which we proved about 3 years ago now, is the opposite, that primes contain lots of arithmetic progressions. So if you take the prime numbers 2, 3, 5, 7, 11, somewhere in there, there'll be a progression of length 3. 3, 5, and 7 is a progression of length 3. There'll be a progression of length 4. Let's see, 3, 7, 11, oh, that doesn't work. Let's see, I can't think more off the top of my head. No, okay, 5, 11, 17, 23 is a progression length of length 4. You can find progression length 5, then 6. It already gets hard. I think if you want a progression of length 6 already, you have to start looking at 3-digit numbers. And in fact, even with a computer, the largest progression that people have actually found explicitly has length, I think, 24. But we've shown that, in fact, somewhere in the primes, you can get progressions of any length you wish. Not infinitely long, but arbitrarily long. There's a progression of length 1 million somewhere, and then somewhere else there's a progression of length 1 billion. There's no progression that's infinitely long, and that's easy to see, but there are ones that are finitely long. Okay, so these two results, they look kind of similar, but in fact, they are proven by almost disjoint methods. In fact, yeah, when we proved this, actually, a famous number theorist came up afterwards and was sort of annoyed that there was they had done 200 years of work on number theory, and we used almost none of it. I think the last result we used, well, it dates back, no, we used one result from like 1900. It turned out we didn't actually need that. So we used very different methods. Since then, we found if you want to get better results than this, we do need to use a lot of stuff like the same type of machinery that Dirichlet used and so forth. So there has been convergence, but initially those are very, very distinct. Okay, so let me talk briefly. I mean, these are both reasonably difficult theorems. I mean, Dirichlet's theorem you can prove in an undergraduate course in maybe like 2 or 3 weeks, and our theorem, there was a quarter. I think it takes about a quarter to present the whole thing, but I can give you some sketches. So the previous results are sort of qualitative results. So let me go back. So both these results say so Dirichet's result tells you that there's infinitely many primes in this progression, and we say there's arbitrarily long progressions in the primes, but we don't say it's not very. This is only qualitative. We don't say exactly how many. This formulation doesn't say exactly how many primes there are up to some n in some progression, and we don't say here exactly how many progressions there are in the primes up to some limit n. So it's only qualitative, and it turns out that if you want to prove the qualitative result, you have to first prove a quantitative result. You have to start counting how many primes you have here, how many progressions you have here, and so forth. It's sort of like if you want to, you have this box full of sand or something, and you want to say that there's lots and lots of sand in this box, you can start looking at all the grains and saying, oh, there's lots of sand here. But actually, the way we actually get a handle on this is that we don't actually open the box, but we just sort of weigh the box, and we say, okay, this box is very heavy, and each grain of sand has a certain weight, and so therefore there's a lot of sand in here. And so the way that both of these results work is that we sort of weigh how many the total weight of all the primes in a progression, and here you sort of weight the total weight of progressions in the primes, and you get some lower bound in both cases on these things, and that's what gives you these results. So this is where the analysis comes in. Once you're talking about bounds, upper bounds, lower bounds, you're doing analysis. So the way we do this, okay, so we need some math notation. So we have to give the primes a weight. So it turns out that we wanted to give every prime a certain weight. And the natural weight to give every prime turns out to be its natural logarithm. So the prime 2 wants to have a weight of log 2, prime 3 wants to have a weight of log 3, and so on and so forth. There's a reason for this I'll get to in a minute. But so we formalize this, we define something called the von Mangold function, a lambda of n. So lambda of n is going to be log of p if n is a power of p, and 0 everywhere else. So lambda of 2 is log 2, so 2 has weight log 2, 4 has weight log 2, 8 has weight log 2, 3, 9, 27, these have weight log 3, 5, 25, so they weight log 5, and everybody else has weight 0. So in fact, most numbers have no weight, like 6 and 18, these have no weight. But basically the primes and a couple other things like powers of primes have some weight. There's a reason for this, for making this funny function. But this is how we tell how heavy every prime is. So definition, another piece of notation, I will keep averaging things. So if I want to talk about the average value of a function, like you take all the numbers from 1 to n, evaluate f from 1 to n and take the average, I'll just call it the expected value of f, or of f from 1 to n. This is a notation that you'll see a lot. Okay, so this is some notation. Okay, so why do we play with this function? It has two nice properties. Actually, it has many nice properties, but okay, so why do we play with the von Mangold function? So the first one is that you all know the fundamental theorem of arithmetic. The fundamental theorem of arithmetic is the fact that every integer can be factored into primes. Like 50 is 2 times 5 times 5. And exactly one factorization for every number up to rearrangement. And that fact is actually, you can encode it as a very nice identity if you take log of that fact. So 50 is 2 times 5 times 5. So that means that log 50 is log 2 plus log 5 plus log 5. And you can formalize that more generally. You take log of any number, and that's the sum of all the factors of that number of this von Mangold function, lambda of d. And so this is, if you just chase the definition of lambda of d, then you see that this is true. And in fact, this is another way to define lambda of d. This is lambda is a unique function with this property. So lambda is the function that encodes the fundamental theorem of arithmetic, and in many ways, it's the most fundamental object that defines the primes. And this identity, once you have this, you can do all kinds of things with it. You can do what's called a Mellin transform. You can Mellin transform this, and then you can do other transforms of that, and so on and so forth. And you get lots of really nice other identities coming out of this fact. Okay, so that's one fact about this lambda. And then there's another really important fact about lambda, which is, so lambda takes all kinds of values. So as I said, it's usually 0, and then every so often it's really big. So if you have a big prime, like say 103, lambda is quite big. It's log of 103, which is what, 5 or something. So it's sometimes small and sometimes big. But on the average, it turns out to have an average value of 1. And that's a great theorem. So the average value of lambda up to any large number n is basically 1 plus a little error which goes to 0 as n goes infinity. But basically, this function, which is very spiky, on the average is 1. And this is a great theorem. This is perhaps the most important theorem in analytic number theory. It's called the prime number theorem. An equivalent formulation is that if you count how many primes there are from 1 to n, the number of primes from 1 to n is roughly n on log n. That's another way of saying it. Or if you pick a number at random from 1 to n, the chance that it's prime is about 1 on log n. Okay, so these are two basic facts about this function. Okay, so Dirichlet's theorem. Okay, so to prove the qualitative version, you want to prove some sort of quantitative version, which looks a lot scarier. But these are much more, in many ways, these more fancy versions of Dirichlet's theorem are much more interesting. They give you actual concrete information about the primes. I mean, the purpose of, well, mathematics in general, but prime number theory is not just to prove theorem after theorem after theorem. I mean, but that's also a way of keeping score. But you want to understand more and more facts about what you're studying, in this case, the prime numbers. You want to, and just knowing that there's infinitely many this or there's lots of that, it doesn't tell you that much. But if you start getting something quantitative, like exactly how many primes there are from A to B and so forth, that's much more information. And so you just want to get as much information on the primes as possible. Dirichlet's theorem, remember, is that if A is coprime to Q, then there's infinitely many primes that have the modulus A mod Q. So there are many ways of stating this. Dirichlet's original proof essentially, he didn't state it like this, but essentially proves this, that if you take the average value of lambda these are all the primes with a certain weight. If you take the primes, but only the primes that are A mod Q, so you restrict to the primes that are A mod Q, and you look at what the average value is, the average value of lambda restricted to the primes A mod Q, and you look at the average value up to some n, then he proves some lower bound. This is bigger than some number which is positive. So the average density of this function is positive, which means that it's going to be positive infinitely often. And that's what tells you that you can have primes at A mod Q infinitely often. This is basically what Dirichlet did. He proved a lower bound on this average. Somewhat later, people, once the prime number theorem was proven, they were able to make this much better. And not only could they say that this average value was bounded below by some lower bound, but they could actually give a much more precise expression as to what this thing is. That this average was actually equal to something very specific. The average value of this thing is actually is actually 1 over phi of q. Phi of q is the number of residue classes that are co-prime to q, plus a small error. And this is what's called the Siegel-Wolfich theorem, and that's a very important theorem in analytic number theory. This error term is not too bad. It's 1 over log to a power, and you can make the power whatever you wish. So it goes to 0 as n goes to infinity, but it doesn't go to 0 all that fast. Actually, there's another problem, that this big O notation, that means that there's a constant here. This constant, once a is bigger than 1, I think, this is what's called ineffective. We know it's finite, but we can't tell you what it is. And there's a long story attached to that, which is there's a slightly, and as a consequence, a lot of theorems in number theory are ineffective. We say that there exists, a solution to some problem, but we can't tell you how big it is or where it is. And it has to do with the fact that we can't track down something very elusive called a Siegel zero, but that's a whole other story. But there's a much stronger hypothesis that will get rid of that and give a much better bound. Rather than 1 over log, it's 1 over square root of n, which is much better number here. But that we can't prove. That's called the generalized Riemann hypothesis, and we can't solve that. Okay, so that's some versions of Dirichlet's theorem. So why do you want these stronger versions? They give more precise information, as I said. For example, if you want to know how many primes there are whose last digit is 3, once you know, say, the Siegel-Wolfich theorem, that tells you, we know pretty much exactly how many prime numbers there are whose last digit is 3. It's about 1/4 of all the primes, n log n, less than n. And similarly, I can tell you how many primes there are whose last digits are 37 or something. That would be what 1 over 40 n log n, and so on and so forth. Or plus an error, and if you had the generalized Riemann hypothesis, I could say the error is really, really small, which it is in practice. I mean, if you take a number, if you take, say, all the primes less than 1 trillion, and you count, you just get a computer to count how many primes there are less than 1 trillion whose last digit is n to the 3, and you compare it with this number, actually a slight tweaked version of this number. But this prediction and the actual count you have agree to like 4 or 5 decimal places. It's actually, this is a really good agreement, which is what the Riemann hypothesis predicts, actually. But that's okay. So my theorem of Ben, that the primes contain arbitrary long progressions, it also has quantitative versions. And as with Dirichlet's theorem, there is a lower bound version, which is what we proved. And then there's a sharp version, which we are trying to prove. So again, here what we're doing is that we have a number k. We want to count progressions of primes of length k. And so it turns out that the quantitative thing to do is to compute some sort of average of the von Mangold function evaluated at progressions. It was just some formula, don't worry about exactly what it is. And what we showed basically was that whatever this number is, it's bounded below as something positive. So we have a non-trivial lower bound on this expression. And once you have that, it's very easy to show that you get lots and lots of progressions of primes of length k. So this result, for k equals 1 and 2, if you want to find progressions of length 1 and 2 in the primes, that's very easy. And so this was done by Chebyshev back in 1850. If you want progressions of length 3 in the primes, that's already somewhat tricky. That was done in 39. And what we did was the general case. But we don't just want a lower bound now. That gives you some information, but it doesn't give you what we really want. And so what we really want is to actually know exactly how many primes there are of length, prime progressions of length k that are up to some number n, and the expected value of this expected weighted value is expected to be equal to some constant g sub k. Traditionally, this g is written in the German factor font for reasons I don't understand, but plus a small error. I'll tell you what G sub k is in the next slide. And so there's a specific number for which this average is supposed to be, and again, this was done again for k equals 1 and 2 a while back. K equals 3, it was found to corporate. Last year, we were able to calculate how many progressions of length 4 there are, and we're working really hard on trying to get 4 and higher. We split the problem into 2 halves, and I finished my half just like this week. And Ben owes me the other half, but that's another story. Okay. Anyway, so what is this G sub k? Well, I'll just give you a flash of formula and not tell you much about it. So it's something called the singular series. What you do is that you don't work with, well, it's actually kind of related a bit to F-Stalk. You don't work with the integers because these are hard. The understanding prime numbers and integers is hard, but you can work with finite models of integers, z mod p, z mod 2, z mod 3, z mod 5. And these we understand very well. And so you can sort of work in, if you like, in the pro-finite version of the integers. You work mod 2 or mod 3 or mod 5, and there we sort of know what should happen. If you work mod 2, almost all primes are odd, so almost all primes should be 1 mod 2. If you work mod 3, all primes should be 1 or 2 mod 3, 0 mod 3, with one exception, and so on and so forth. So the primes mod p should be distributed in all the residue classes except 0 mod p, and so there's and so you can work that out, and there's sort of an analog of this more mangled function mod p, and so every mod p gives you what's called a local factor, and then what you do is you just take all those local factors and multiply them together, and this gives you your guess as to what's going on for the integers. So some of the philosophies that the integers should be behaving like, if you like, the pro-finite version of the integers, so all these z mod p's put together. So this was all conjectured by Hardy and Littlewood 80 years ago and backed up by a lot of numerical evidence. So there's this thing called the Hardy-Littlewood prime tuples conjecture, which predicts how many patterns of almost any sort should exist in the primes. So one funny thing about number theory, as opposed to other fields of mathematics, is that we can't prove everything we want, but we can conjecture things that we want really well. So almost any question about the primes, we can say very confidently whether it's true or false, whether something's true about the primes, and we have lots of numerical evidence, lots of heuristic evidence, but we can't prove most of that. Our ability to conjecture is somehow about 100 years ahead of our ability to actually prove things. So, you know, I mean, we have all these conjectures, and we're pretty much like 99% certain they're all true. Right? It's just we can't prove any of them, which is, well, it's not that bad a situation to have. It's better than having no conjectures at all, but we'd like to have a bit more progress. Anyway, so there is this conjecture called the prime tuples conjecture, which basically tells you how often, it predicts how often a certain pattern of primes should appear. And it's very general. It predicts, for example, how many twin primes there are up to some number n, and it predicts there's infinitely many. It predicts how many ways you can write in even numbers of sum of 2 primes, and it will predict the go-back conjecture. It predicts all kinds of things. And we would really love to prove this conjecture, and we haven't done so yet. Okay, so these are these numbers, just to give you some flavor of what these numbers are. So these numbers, so G1 is 1, G2 is 1, G3 is 1.3, G4 is 2.8. So there's very explicit computable numbers. These are sort of, this tells you sort of the average weight of all the progressions of the 4 in the primes, the average weight of all progressions of the 3 in the primes. Yeah, so for example, one of the results we have is that if you want to count how many progressions of primes there are of length 4 less than n, it turns out we know pretty much exactly how many primes there are now, of how many of these patterns there are. It's about 0.476 n squared over log 4n. Okay. And so we have this very quantitative information, and there's lots of other results like this. It's just a sample of what we can do now. Okay, so going back to multiplicative prime number theory, the way we prove things in multiplicative prime number theory, like Dirichlet's theorem, is we rely a lot on lots and lots of identities. So lots of formulas, and which are very deep, and well, some are deep, some are not so deep, and connected to all kinds of lovely areas of algebraic number theory, you know, Galois theory, and so forth. Again, connecting to F-Stalk. But so, for example, to prove Dirichlet's theorem that if A is coparameter Q, then it's infinitely many primes mod Q. Essentially, if you understand each of these, if you understand what these 4 equations mean, then you can prove Dirichlet's theorem. Basically, you're done. But I'm not going to prove Dirichlet's theorem here. I just wanted to show you, or I just point out that you have 4 identities. And if you can understand these 4 identities, then this is basically all you need. So this identity, this is the multiplicative Fourier inversion formula. So you're trying to count primes, which are A mod Q. You can write that as what's called a character sum. So then you're faced with these funny things, lambda and chi n. So you mess around with this a little bit, and you sum it and whatever. And it turns out that this thing is equal to something very nice. It's equal to L prime minus L prime over L, where L is something called an L function, strangely enough. I won't tell you what that is. But once you have this identity, you can apply complex analysis, and you can solve this. You can sort of solve for this in terms of this. And there's a way to do that by Cauchy's theorem. And what it tells you, roughly speaking, is that this expression here, which is what you need to count primes and progressions, is equal in some sense to a very explicit formula, which is actually the sum of stuff over the zeros of this L function, plus some other things which I won't talk about. Why is this equals in quotes? Well, it's sort of actually the same problem as in Richard's talk. This sum doesn't actually converge. But we have ways to renormalize it and massage this, and we work in distributions and so forth. This actually can be made sense if you are willing to suspend enough disbelief. This tells you, this formula tells you what the primes are doing as long as you know what the zeros of this L function are. And it turns out that all the zeros are easy to deal with except the 0 at 1. When rho is 1, then this thing cancels, and that turns out to be a really big problem. So you need L1 chi to be non-zero. And then what comes in is this amazing formula called the class number formula, which expresses L1 chi in terms of a bunch of algebraic stuff, which comes from actually the Galois extension of the integers using this character chi. Okay, so there's all kinds of stuff in here, but the basic point is that none of these numbers here are 0. And so whatever this formula is, it tells you that this is non-zero, and so 1 is not a 0. And so actually, once you have these 4 facts, you get Dirichlet's theorem. So it's an amazing proof, but I just want to illustrate that here. Okay, but it's very algebraic. So what we do, we sort of use almost the opposite philosophy. Somehow, most of the progress in number theory in recent years has been by pushing this algebraic viewpoint really, really hard, and it had some really good results. Fermat's last theorem was proven by really sort of hardcore algebraic number theory, which is connected in some ways to what I discussed. And there'll be lots of other progress coming out of that too. But once you go to additive prime numbers, some of our primes really don't want to be added. Or at least once they do, you lose all the algebra, and you have to just use analysis. But okay, it's good for me because I don't really do algebra. I do analysis, so I'm much more comfortable with this type of number theory. So additive prime number theory is much more analytical, much more sort of statistical. You don't ask for magic identities about the primes because they tend not to exist when you look at additive structure. Instead, you ask for statistical properties of the primes, not what the primes are exactly equal to, but sort of how they behave. So how they correlate with things, how they discorrelate with things, especially additively structured things. So, for example, a good example is you take the primes and you ask, as I said before, how do the primes interact with, say, this complex exponential? This is a linear phase, e to a linear function here. And you can ask, how do the primes, do the primes do anything interesting at all with respect to this function? How do you define interesting? Well, there are many ways. One thing you can do is that you can just sum the primes of this weight, e to the alpha n. This is very much like this prime exponential sum I talked about earlier. And so you can ask you can sort of correlate the primes with this funny function, and you ask, is there any correlation at all? Do the primes look like this function, or do they not look like this function? And it turns out sometimes they do, sometimes they don't. Depends on what this alpha is. If alpha is rational, which is a over q, then this is a non-zero expression. It's what's called a Ramanujan sum. And well, there's a formula, but never mind the formula. It's just some very algebraic understood expression. But if you're trying to correlate lambda with something irrational, you get 0. So this is a very typical fact. And this is in fact this particular fact is very important in the theory. Versions of more quantitative versions of this, but what you see is that so what this is telling you is that sometimes the primes behave like e to the alpha n. So the primes have some connection with exponentials when your phase is rational and not when it's irrational. And so you see this dichotomy. And this dichotomy seems to be the tip of the iceberg of something much bigger that we've sort of discovered in the last few years. So it comes from, so it's, what seems to be the case is that if you want to understand multiplicative number theory, you have to learn algebra. Okay? You have to learn number field extensions, Galois theory, lots of really sort of high-tech stuff. If you want to do something in additive number theory, you have to learn a different type of mathematics, and in particular, you understand dynamical systems or ergodic theory. How do I describe dynamical systems? Right? It's just, just the evolution of any system, anything which moves around. Studying anything with a time variable, basically. And so, in particular, what I just talked about with these phases, you can recast. It seems that what you should be doing is you should be understanding it in terms of what's called the circle shift map on the circle. So the unit circle, you can look at the shift map by rotation by alpha. So you pick some angle alpha and you just rotate by alpha. And so that gives you a point you can rotate and rotate and rotate and rotate. That gives you a whole bunch of points. And depending on what your angle is, this rotation does different things. For example, if alpha is rational, suppose you take a circle and you just decide to rotate the circle by a quarter rotation, like 90 degrees, again and again and again. If you do that, that's a very boring dynamical system. You take a point, you rotate 90 degrees, 90 degrees, 90 degrees. All you do is you just get 4 points over and over again. Okay? You don't get to visit anybody else in the circle, you just get 4 points over and over again. And so we say that this flow is a periodic flow. If instead you rotate by an irrational angle, for example, if you rotate not by a quarter rotation, but say 1/2 pi of a rotation, so that's 1 radian, that's about this much. You rotate like this, rotate 1 radian, 2 radians, 3 radians, 4 radians. Because 1/2 pi is irrational, you never go back to where you start. And in fact, what happens is that you fill out the entire circle. Well, that's not quite true. You fill out what's called a dense subset of the circle. You get arbitrarily close to any point in the circle. Okay, and that, because of that, we say that this flow is ergodic. In fact, it's a bit better. It's what's called totally ergodic. That's a technical thing. So you can see that some dynamical systems, so different dynamical systems have different sort of personalities. Right? Some are periodic, and some are the opposite of periodic, is ergodic. And the primes sort of like the periodic systems, but they want to have nothing to do with the totally ergodic systems. What that means, it's like if you go to the quarter rotation, right, you go rotate by 1/4 rotation, and you take a point, but you don't look at every orbit. You look at this. You look at the prime orbits. You look at the second point, third point, skip the fourth point, go to the fifth point, seventh point, 11th point, 13th point. So if you only take the points, if you only take the prime numbered points of the orbit, you don't get to visit all 4 points. In fact, you only get to visit 2. Well, I mean, because the primes are odd, except for one exception, and because of that, you don't visit all 4 points of your orbit. You only visit 2 of them. And so when you look at what the primes how the primes sort of interact with this quarter rotation system, they have some detectable bias. They don't like 2 of the points. They want to cluster on only the other 2 of the 4 points. And so there's a notable bias when you correlate primes with irrational rotation. And so some irrational rotations become very important in understanding this whole subject. But if you instead look at irrational rotations, it turns out that there's no such conspiracy, that the primes don't care. They want nothing to do with an irrational rotation. If you rotate by 1 radian at a time, 1 radian, 2 radians, 3 radians, 4 radians, so that will distribute itself uniformly around the circle. If you look at the prime points, second point, third point, fifth point, seventh point, it turns out those points will also distribute uniformly around the circle. There's sort of no distinction. And so the primes, they basically just don't care about the system. And this also turns out to be important. So there's sort of this, in recent years, we've sort of understood now how to approach problems in prime number theory, in additive prime number theory, which is basically to work out what dynamical systems the primes like, what they correlate with and what they don't correlate with. And once you figure out all that information, you can work out just from that how they interact with various dynamical systems. you can then start counting how many patterns of a certain type there are in the primes. So it's just some very, very vague philosophy here. So the primes from 1 to n, we know how many primes there are. They have density about 1 over log n. So you take the numbers from 1 to n, the primes inside are just some sort of random, or some set inside here, and we know how big the set is, but we don't know how the primes are distributed. Maybe they, for example, the twin prime conjecture, maybe they like to be close to each other. Maybe primes want to be next to, distance 2 apart from each other, but maybe they actually want to repel each other. They don't want to be close to each other. Maybe after a while there are no twin primes. We don't know. So we don't really know what this set is doing, but the philosophy that's emerging is that by default, I think what the primes want to do is it's hard to, well, of course, you can't assign these are not animate objects, but this is useful for thinking about things. So the primes somehow want to behave randomly. Okay, they want to give every number an equal chance of being prime. If they actually were random, then you could do all kinds of things. Like if you had a random set of from 1 to n of density 1 over log n, it's really easy to count how many twins there are. Like if you knew the primes distributed randomly, it's not hard to argue that the number of twin primes, say from 1 to n, should be roughly this number. So they sort of want to be distributed evenly, but they're not, and so these sort of they're constrained. They have some patterns, or like conspiracies. They have arranged to organize themselves in certain ways. For example, primes, almost all primes are odd. Okay, so because of this, so all even numbers are basically automatically excluded from membership in the primes. This is why, for example, you can never find any adjacent primes, p plus 1, other than 2 and 3. Although on the other hand, since you're squishing the primes into the odd numbers, that should increase the number of twin primes, because if p is odd, then p plus 2 should also be odd. And so somehow this conspiracy should reduce some statistics but increase others. Okay, so we do know that there are some patterns that the primes have. They're all odd with one exception. They're all adjacent to a multiple of 6 with 2 exceptions, and so on and so forth. And so it seems like the way to approach these sort of problems is to try to figure out all the patterns that the primes have. Like what do the primes do? Right? Okay, so list all the possible correlations that the primes have with various things, all the correlations that could actually affect what you're actually working with, work out all these things are. And once you have all that, you should be able, in principle, to compute your original problem. For example, computing, well, we can't yet compute twin primes, but we can compute other things now. We can compute things like how many progressions of a certain length there are in the primes, or how many ways you can write numbers. We can't, for some reason, we can't compute how you can write numbers sum of 2 primes, but we can compute how we can write numbers sum of 3 primes. There's a good reason for that, which I'll get into here. But there are many statistics that you can work out once you know sort of what the primes, what conspiracies that the primes will exhibit, and which ones that they have nothing to do, which ones that they don't. And so basically we want to know how the primes interact with dynamical systems, and that seems to be the way to move forward in this business. We have, as I said, we know how to conjecture all kinds of things. We believe that the primes, the only conspiracies that the primes actually have should be the ones that actually are sort of obvious, the ones that come from simple algebra. So as I said, the primes are almost all odd, and that's obvious. It comes from algebra. The primes are almost all coparameter to 3, so forth, and that's obvious. And the primes are all positive. Actually, there's another obvious fact, but it's important. But apart from these sort of obvious things, there should be no special conspiracies in the primes that we don't know about. There was a book by Carl Sagan called Contact, which got made to a movie starring Jodie Foster. In the movie, what happened was that Jodie Foster contacted aliens. She went off and visited the aliens, and then she came back, but she had no physical proof that she had actually visited the aliens, and so no one believed her when she came back. In the book, actually, the story is a bit different. So the protagonist goes to outer space or whatever, talks to aliens, comes back, and again, she has no physical evidence of her visit, but she does have proof that she contacted alien intelligence. And the proof was that the aliens told her that they had found a secret message encoded in pi, that if you expand pi to 1 trillion digits and you look at the trillionth or after the trillionth point, eventually, so the digits will be random, and then eventually there will be this lovely pattern inside the primes, which you can arrange into some sort of picture, which they believe to be a message from the creator of the universe. And so, and this was how she could prove that she had contacted aliens, because she came back and she then set up a computer to check this, and then they found the patent. And that was the end of the book story. That never made it into the movie. Somehow math never gets cut out from the from movie scripts. But anyway, I mean, it could be that the primes, they look kind of random, and then like eventually they all start, for example, favoring the digit 3 or something. Or all primes start having lots of 3s in them, right? That shouldn't happen. Actually, maybe that one we can prove. But okay, but there are lots of patterns which might be true. We can't prove it. As I said, it could be that the primes, after a while, they just don't want to be close to each other. The primes never want to be within distance 2 of each other after a certain point. We can't stop that from happening. We don't expect it to happen. That'd be very weird. But we can't prove it yet. But we believe that the primes have no other patterns other than those that we already know of. And based on that belief, which we can, based on that belief, we can predict all kinds of things about the primes. We can predict almost anything about the primes if we believe that they are random up to all the patterns that we already know about. And that would predict all kinds of things. The Riemann hypothesis, twin prime conjecture. This heuristic predicts, this is the source of all our predictions. And it has some very impressive numerical evidence, and also now recently some theoretical evidence as well. But it's still, I mean, this is not even a conjecture, this is just a belief, and we have no way of actually proving this yet. Let's see, I'm not sure I want to talk about this. Yeah. Let me skip a lot of this. Well, let me just say a couple of things. So, it turns out that the more complicated the pattern you want to count in the primes, the harder you have to work, because it turns out there are more and more different types of conspiracies. There are more and more dynamical systems that could conceivably jump in and distort the count of how many of these patterns there are. There's more and more stakeholders somehow in the whole business. If you want to count progressions of length 3, then you always have to deal with these things called what I call linear conspiracies. Like if you want to count how many times a pattern n plus r n plus 2r appears, there are these linear conspiracies you have to deal with. And so what happens, so never mind the primes, it's a more general question. If you want to count a function of n, a function of n plus r, a function of n plus 2r, f has some average value, which I call EF. G has some average value, which I call EG, and H has some average value, EH. All things being equal, if you expect these things to be sort of independent, this product should be sort of like the average of F times the average of G times the average of H. This is what you expect if there's nothing funny going on. So this funny expression should sort of split into these factors. But as you know, you can't actually interchange products and sums. Some of our freshman algebra was so much easier if you could. But you can't, that is false. That this expression f of n, g of n plus r, h of n plus r doesn't always factor. And the reason is because of these funny conspiracies. That if you set f to be a certain linear phase function, g to be another linear phase function, and h to be another linear phase function, there's a certain identity that connects n plus r, n plus 2r, and what it does is it makes all these phases cancel, and it makes this average non-zero, even though these functions have average 0. Never mind where it comes from, but well, it's related to the following very, very simple fact. If you have a function of a line, and you know what its value is at one point n, and another point n plus r, if you know if you know 2 points determine the line, and then at the third point you know actually what you can extrapolate, and so this gives you some sort of constraint between behavior at 3 different points in arithmetic progression. And every time you have a constraint, that distorts, that's a possible conspiracy that can distort your statistics. So you always have to deal with these linear exponentials. And so there's a whole theory of this, it's called the circle method, which I guess I will not talk about, I don't have time. Okay, so I'll skip all that, blah, 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 okay. Once you go to higher progressions, like progressions of length 4, it turns out that you not only have to accommodate all these linear conspiracies, but then there's these other conspiracies that sort of climb on board and want to be represented too. So if you want to count progressions of length 4, Then there's a quadratic conspiracy that comes in. That's supposed to be a 2. That's a typo there. This is really the fact that if you take a quadratic polynomial, like a parabola, if you know the value of a parabola at 2 points, that doesn't tell you what happens everywhere else. But once you know the value of a parabola at 3 points of progression, you can extrapolate and get the fourth, Lagrange interpolation. And so quadratic functions induce a constraint between progression of length 4. And it's because of this fact that you really have to deal with quadratic functions as well. You have to understand what the primes are doing with respect to quadratic functions to understand progression of length 4. And that's very annoying. In fact, it's even worse than that. There's, let's skip this. It's not just quadratic things. It turns out that, you can classify all the dynamical systems that cause trouble for progression length 4. And that this turns out to be something called a two-step no system, which it has to do with two-step no-important Lie groups, which maybe I think I'll just completely skip because it's not elementary. And then if you wanted to do progression length 5, you had to do with three-step no-important groups, and it just gets worse and worse and worse. But we have at least just very recently, Ben Green and I understood these two-step no-important no manifolds and how they collate with primes. This took 3 papers, each about 60 pages, but we managed to do it. And as a result, we can do things like count progression length 4, and that is where we're at right now, and we're working now on progression length 5, 6, and so forth, and other patterns of this type. There is a connection to a really nice theorem called Ratner's theorem, but I think I don't have time for this, and it's really quite technical. So maybe I think I'll stop here. So thank you very much. Yes.
The alpha that you have in that Hardy-Wood function, at one point you had a relationship where it turned out to be rational and you get a non-zero value, irrational, you got a 0 value. But in the other uses, are there preferred types of alphas?
Yes. Again, rational alphas give you. It's ultimately there is some sort of concept of a rational flow. Basically, if the orbit is finite, then you get a strong correlation, and the orbit spreads out over an infinite set. Then the correlation is 0. That's basically what happens. So this Ratner theorem, which I'm not talking about, describes what orbits on a dynamical system look like, and they either look like finite sets or they're distributed inside some bigger high-dimensional object.
So there isn't anything more refined than either rational or irrational as far as that.
As it turns out, yes. So this is so I mentioned earlier that the only conspiracies that we expect the primes to obey us are the obvious ones, and this is a very concrete manifestation of this fact that we know that the primes are strongly biased towards periodic systems, but almost any non-periodic system, the primes have no correlation with, and this is what underlies all these results.
I have a question that's submitted by my students. Why in the world would anyone study prime numbers?
Well, there were. Okay. Well, it's a very classical subject. It's one of the first things that the ancient Greeks studied them. So there's a lot of classical interest in them. Hardy was once very proud. So he worked in number theory, and he was boasting, in fact, that he was working in the best type of mathematics, the purest form of mathematics, and mathematics would have no application whatsoever. And he was very happy about this. He didn't want to be tainted by these applications. And then several decades later, people found out that these prime numbers are very, very useful in cryptography. And so, your bank transactions over the internet or through ATM machines and so forth, they're all governed by prime numbers, and in the belief that certain operations connected to prime numbers do behave randomly in a certain sense. If there were secret patterns in the primes that you didn't know about, but I did, I could potentially crack whatever communication you have with your bank using these patterns. And so it's good to know that we want to know that the primes have no special patterns in them. What I do here is not directly related to cryptography, but there are some weak connections. There are certain cryptographic schemes which have recently been proven to be at least weakly secure based on stuff which is vaguely related to this. There are some interconnections, well, I'm a pure mathematician. You know, it's I work on things because they seem to produce fruit, and whether well, they produce more pure mathematics, and then hopefully eventually they'll connect to something applied, which happens actually more often than it happens surprisingly often. But it's not something that you sort of force. You just sort of explore what's productive, and often you get a nice surprise.
Yeah, maybe I can comment on the Hardy story. So the reason Hardy was proud of it, that his math had no application, he said, at least my math cannot be used to make any wars. It was a time where the nuclear bombs were invented and so on. And of course, cryptography is now used in wars.
Yes.
Using supercomputers, is there ever a case where you might look for statistical evidence of a pattern in the primes and from that try and explain it rather than posit a theory and then try and look for evidence?
There is a lot of work on numerical number theory. So the Riemann hypothesis has to do with zeros of the zeta function, and people have computed trillions of zeros of the zeta function, and actually a lot of really good conjectures came about initially from numerical evidence, things like gap spacings of these zeros and so forth. Computers in this business, they're not as well. They do produce some impressive results, but the thing is, the best computers today can basically count primes, say, up to about 10 to the 15 or 10 to the 18 if you really push it. But a lot of phenomena we actually care about, you can only start manifesting itself at much bigger scales, like 10 to 100 or something, which is well beyond what a modern computer can do. I think there was some famous conjecture of Littlewood about the number of primes less than x was always thought to be, I think, either less than or bigger than something called the logarithmic integral of x, and had very impressive numerical evidence that this was the case. But eventually they proved that this conjecture was false. Eventually, but I think eventually it was like 10 to the 1,000 or something. So sometimes numerical evidence, if it's done wrongly, it can be misleading. But people do use it. So.
Have you looked at the corresponding questions for, say, Gaussian primes?
Yes. My theorem of Ben is that the primes contain arbitrarily long arithmetic progressions. So I had a later paper saying that you take the Gaussian primes. These are so the Gaussian integers are like ordinary integers, but with a complex number. So like 3 plus 5i is a Gaussian integer. There's a notion of Gaussian primes, the Gaussian integer that can't be factored into smaller Gaussian integers. So these form sort of like stars. You can think of them as like stars in the sky. So again, another movie connection. There's a movie, Beautiful Mind, where at one point John Nash wants to impress his girlfriend. So he asks his girlfriend to name any shape at all, and she says an umbrella, I think. And so he looks at the night sky, he looks a little bit, and says, okay, I see an umbrella. And so he picks out like 12 points which form an umbrella, and she's very impressed. And so you can show that this is true for the Gaussian primes. If you think of the Gaussian primes as a whole bunch of stars, given any shape, like an umbrella, with rational coordinates, but okay, given any shape, you can find somewhere in the constellation of Gaussian primes, a shape which is exactly the proportions of this umbrella. So yeah, so the Gaussian primes contain constellations of any shape. Yeah.
My question is similar to the one about pattern, and I'm curious about the importance of the number 2 in prime number theory, whether multiplicative or additive, because with the exception to the difference between any two prime numbers is a factor of 2.
Yes.
So I've always thought that the real pattern is not about the sequence of primes per se, but about the sequence of the differences in prime numbers.
Right.
So I don't know if that's implicit in what you do, because I'm not a mathematician, but that's always struck me as
Yeah. So 2 often demand special treatment in this business. Yeah. And so one thing we often do is that we take the primes, we subtract 1, and we divide by 2, and that's sort of so the primes are all odd except for 2. But if you subtract 1 and divide by 2, then you get a new sequence, and this sequence is both even and odd. And what you've done is you've somehow projected out 2, so 2 no longer exists somehow as in a certain sense once you do that. Every time you actually know of a pattern in the primes, there's a way to sort of quotient it out, and you can sort of rewrite your problem to ignore it. As Donald Rumsfeld said, it's not the known unknowns that are the problem, it's the unknown unknowns. It's the It's the patterns that we don't know whether they exist or not, which cause the problems. But yeah, but things like being odd, copying of 3, we understand those very well. We know how to deal with them.
Okay.